You know, in physics, we usually start with the big rules, the fundamental laws, and then we build everything up from there. But what if those rules aren't really the starting line? What if we can actually dig deeper? Today, we're going to look at a really fascinating new theory that tries to do exactly that. It doesn't just describe a law of nature, it tries to derive it from something way more fundamental.
All right, let's start with a question we've all heard since grade school. Why do opposite charges attract and like charges repel? It's pretty much one of the first things we learn about how the physical world is put together.
And the answer you get, right, is Coulomb's law. It's the official rulebook for electricity, spelled out in the language of math. It works, it's super precise, and for hundreds of years we've basically treated it as, well, a fact of life, a rule we found, not one we really explained.
Okay, but this is where it gets really mind-bending. What if that foundational law isn't a starting point at all? What if it's just an outcome, an echo of something much, much deeper and simpler? That's the rabbit hole we are diving into right now.
The proposed answer to that question comes from something called the Harmonic Scale Framework, or HSF for short. And it asks us to reimagine our entire universe, not as a bunch of tiny particles and mysterious forces, but as a giant symphony of waves.
So what is this thing really? Well, at its core, the HSF suggests that everything we can possibly measure, from a single electron to an entire galaxy, is just a different kind of ripple, a stable pattern on one single, universe-spanning wave. Think of it like this. You've got one grand piece of music, and everything we see is just different notes and chords being played. This idea really flips the script. In this model, particles aren't little dots. Nope, they're more like stable, vibrating patterns, kind of like the standing wave you see on a plucked guitar string. And what about fields, like an electric field? Well, those are just the waves that travel outward from those patterns. And crucially, the HSF says all of this is happening inside a universe that has a very specific shape, a slightly squashed sphere, which turns out to be the perfect container for all these different waves to exist in harmony.
And this image here gives you a really good feel for the concept. It's not about lonely little particles floating around in an empty void. It's about one single interconnected wave system that shows up in different ways. Sometimes it looks like a stable particle pattern, and other times it looks like a traveling field wave. It's all the same stuff, just doing different things.
Okay, so that's the big picture. A universe of waves. Cool idea. But here's what makes it really compelling. The HSF doesn't just claim the universe is made of waves, it actually uses that very idea to derive, from first principles, one of the most bedrock laws of physics we have.
Here's the recipe. You start with a standard issue wave equation. Then you plug in those unique HSF boundary conditions, that slightly squashed sphere we just talked about. And when you solve the math for the simplest possible case, what they call the static zero-frequency limit, bam, out pops Coulomb's law. It's not an assumption you put in at the beginning, it's the answer you get at the end.
And this quote from the source material just nails it. Coulomb is the zero-frequency limit of K2 wave propagation. It's basically saying that the fundamental force of electricity we all know and love is just a special case of wave behavior. It's what happens when these particular waves stop, well, waving. It's the leftover hum.
Look, deriving old laws is one thing, and it's seriously impressive. But for a theory to be truly great, it has to do more. It has to predict something new, something we can actually go out and test. And HSF does just that. It makes 7 specific predictions that go beyond our current understanding.
Let's start with prediction number 1. And this one, it goes right after something we all learned in class. We're taught that the electric field from a single charge radiates out in a perfect sphere. Well, HSF says not quite.
So on the left, you've got the standard textbook picture, nice and perfectly round. But on the right is the HSF prediction. Because the universe's boundary isn't a perfect sphere, the wave solution, the electric field, can't be perfectly spherical either. The theory predicts a tiny but very specific 2% distortion. It's a small but distinct fingerprint.
All right, if you thought that was a big deal, the next prediction is, well, it's on another level. It suggests that one of the numbers we consider to be a fundamental constant of nature might not actually be constant at all.
HSF predicts that a physical constant called epsilon naught, which basically sets the strength of the electric force, is actually drifting incredibly slowly over time. Now, the rate is just mind-bogglingly small, about 1 part in a quintillion per year. But here's the thing.
It's a specific number. It's a target we could, in theory, go hunt for.
And it doesn't stop there. HSF also offers a potential reason why electric charge comes in little packets, like the charge of an electron, instead of being some continuous goo. It predicts that the famous inverse square law should bend a little bit at super short distances. And it even says that in really intense fields, 2 plus 2 might not perfectly equal 4. Electric fields might not add up in the simple way we expect.
Okay, I know. These are some seriously wild ideas. But are they just a cool story, or is this actual science? Well, the difference is testability. Can you prove it wrong? So let's look at how we could actually go search for these crazy effects.
And this is where it gets real. For each of these big predictions, there's a proposed experiment. To find that non-spherical force, you could use an incredibly sensitive rotating device called a torsion balance. To spot that drifting constant, you'd need to link up atomic clock networks and watch them for a decade. This isn't just wishful thinking, it's a practical experimental roadmap.
And this is the most important part. Yes, the effects they're predicting are ridiculously tiny and super hard to measure. But, and this is a big but, they are specific. The theory gives us actual numbers and patterns to look for. And that means it's falsifiable. It makes bold claims that an experiment could actually shoot down. And that, my friends, is the hallmark of real science.
So, after all that, what's the big takeaway from our dive into the harmonic scale framework? What's the bottom line here?
The ultimate takeaway is this potential shift in how we see our universe. HSF proposes that the laws we've discovered, like Coulomb's law, might not be these random, arbitrary rules that the universe just decided to follow. Instead, they could be the inevitable, logical consequences of a simpler, deeper reality. In this case, a reality made of waves.
And that's the question I want to leave you with. Whether HSF turns out to be right or wrong, it forces us to ask, what would it mean if our most fundamental laws are just the surface, just the ripples from a much deeper reality we haven't even seen yet? What else out there are we just describing when we could be deriving